So Paythan Chandrana is a PhD research assistant in the Intelligent Circuits Architecture and System Lab under supervision of Dr. Ramtin Zan at University of South Carolina. Since joining the lab in the spring 2021, Paythan has authored and co-authored 5 papers and 1 book chapter on data-intensive and compute-intensive applications. His current research interests consist of neuromorphic computing topics such as efficient spike coding algorithms and neuromorphic hardware design, which aim to significantly reduce power and energy consumption on machine learning workloads. In addition to his research studies as a PhD student, Paythan is also an instructor of the Unix Linux fundamental courses in the Department of Computer Science and Engineering, where he teaches over 100 students. So I think with that, we can start the presentation. Paythan, floor is yours.
Thank you for the introduction. Can you hear me all right? Just want to make sure everything's
Yes.
Okay.
Yes.
Great. So thank you for the introduction. Good morning, everyone. So I am going to briefly go through kind of a quick introduction and some my lab's introduction, as well as then I'll start presenting the work. So as Dr. Angizi said, I've been at the University of South Carolina since 2019. I received my bachelor's in engineering of computer engineering at the University of South Carolina. And then I started as a master's student, and I eventually found neuromorphic computing because I was interested in biology and how biology can be used in the field of computer science, as well as how computer science can actually draw inspiration from biology to help with computation and stuff. And then I joined the ICASC lab under Dr. Zand in 2021, and since then I've co-authored many papers and a book chapter. So ever since I've started my PhD, I've kind of had a couple different impacts in mind, teaching at a kind of a local impact to the local community, as well as kind of research to have a more widespread and diverse impact. And my goal after my PhD is to get pursue a tenure track position at some university. So about our lab is the Intelligent Circuits Architecture and Systems lab at the University of South Carolina. We have 4 PhD students, 2 master's students, and 2 undergraduate students right now. Right now, we're heavily interested in neuromorphic computing and AI acceleration, with particular emphasis on making it more efficient, as well as faster computation in a more energy and power efficient way, sustainable way. So from there, we have several collaborations with Intel, specifically the Intel Neuromorphic Research Community, which gives us access to chips like Loihi to run experiments, as well as do research in the neuromorphic community. We also have a collaboration with Juniper Networks, Van Robotics, and Xilinx for FPGAs. And we almost weekly publish course lectures, including my lectures that I give on YouTube, and we can be found on social media pretty readily. So with that in mind, I'm gonna go ahead and start presenting the paper. So my paper, Energy Efficient Deployment of Machine Learning Workloads on Neuromorphic Hardware, really focuses on trying to kind of somewhat address some of the deep learning challenges that we see today, mainly in that deep learning typically involves high power and energy consumption compared to some things like neuromorphic hardware. So in some cases, we can have significant latency. With deeper networks, you typically incur a significant latency cost in your deep learning or machine learning use case. And then obviously you have a ton of different constraints as far as that because of the power and energy consumption. And these constraints are mainly introduced due to the nature of deep learning on traditional hardware such as GPUs and TPUs because of their floating point values being passed along from layer to layer with multiply accumulate operations, which are again costly in terms of latency as well as power. Okay, so with that, a quick introduction to neuromorphic computing. So neuromorphic computing is kind of considered to be the third generation of artificial neural networks, which use spiking neural networks. Spiking neural networks are different from the traditional neural networks that we've come to know in deep learning because they use discrete times or discrete spikes or action potentials to pass messages or information from layer to layer. These spikes are discrete and only happen when stimulus is presented to the network. Basically, you have an input spiking neuron like this one. It does some spikes, it goes over a weighted connection to another neuron, and then after that neuron reaches a certain threshold, it spikes as well. So they're biologically inspired off of our own brain neurons, which work this in a very similar way, where after so much stimulus is received, it fires. The neuron fires, it passes and propagates the information throughout the network. And this is really nice because it gives some benefits like event-based computing, low latency, and then, of course, low power and energy consumption, because you're only ever consuming power whenever there's a stimulus or another spike or information being passed into the actual network, versus in traditional deep learning workloads, you typically consume power much more frequently. Okay, so there's a couple pros and cons to neuromorphic computing. The main ones being that obviously neuromorphic computing is significantly reducing latency latency in a lot of cases compared to deep learning approaches, while also achieving comparable accuracies. However, neuromorphic computing, because it is somewhat new in terms of hardware design and hardware acceleration, there's still a lot of current research going on how to efficiently train the algorithms for especially deeper networks, as well as there's some definitely disadvantages to being such a new design. There's like non-trivial network design. You have to do a lot of parameter optimization, and there's obviously not that much hardware support yet. There are some chips, I think it was 2014, IBM introduced True North. Now we have Intel Loihi, and there's also Spinnaker. But for the most part, they're kind of research level hardware designs, not consumer level yet. All right. So with that in mind, so why do we need these things like Loihi and neuromorphic computing? The biggest use case is for things like edge computing. And as of late, more and more hardware devices are coming out that are really trying to support edge cases like robotics, aerial drones, things that are power constrained and latency constrained. These things, typically, these robots or drones or wearable devices usually use something in the form of computer vision or image classification to do some kind of work. So that's where our paper kind of focuses, is on image classification at the edge, to try to achieve a decent accuracy while reducing as much energy and power consumption as possible. So we do 3 different data sets. We do the MNIST handwritten digits data set, the fashion MNIST clothing, and then the ASL alphabet. And these are, again, to try to benefit these portable devices or power-constrained devices so that they're using as little power as possible compared to the traditional deep learning approaches. All right. So some of the edge devices that have emerged in the last couple of years include like the Intel Neural Compute Stick, the Corel Edge DPU, Jetson Nano, and of course Intel Loihi, which is a neuromorphic based processor or chip. In this work, we really just focus on Intel Neural Compute Stick as well as Intel Loihi. So Loihi, again, is neuromorphic, so it runs on action potentials or spikes and is very power efficient. And the Intel Neural Compute Stick operates on floating point 16 precision values. And then most of these devices, again, most deep learning devices, except for Loihi, really kind of take their power and latency savings from quantization or approximate computing approaches, which try to minimize the data to some extent, as also prune some of the unneeded data so that you can see power efficiency and energy gains. All right, but like I mentioned earlier, neuromorphic computing is kind of constrained in that it's fairly new compared to deep learning, and that there's still a lot of research going on to how to properly train and learn these networks. So in order to kind of circumvent this kind of limitations, especially with deep spiking neural networks, we use an approach that converts deep neural networks into spiking neural networks using the SNN conversion toolbox proposed by Rockhauer and Bodo in 2018. So what this allows you to do is basically train a conventional deep neural network or convolution neural network in something like TensorFlow or Keras, and then it allows you to convert each of those neurons in a one-to-one manner somewhat automatically to get the power efficiency gains. So there are some caveats to this, mainly that not all design choices are necessarily supported. The authors are kind of limited to what they can support, as well as what is possibly feasible to support in spiking neural networks. For example, max pooling specifically is not really able to be accurately represented in the spiking domain because of max pooling's nature, whereas it is achievable in conventional deep neural networks. But we'll see later that max pooling itself isn't necessarily needed. So, and then we also, obviously, because we're converting something, it's not necessarily the most optimal in terms of the results you get, because we're kind of doing a hybrid approach that's not necessarily perfect, but it is still attaining the better, significantly power reductions. Okay, so, and again, these conversion steps is basically you just train a deep neural network, you convert it to an SNN, and then you deploy it on neuromorphic hardware to get realize those power efficiency gains. All right. So in this case, in this work, we actually use a version of the VGG network, and specifically we use a variant that we call VGG9. It has 6 convolution layers, it has ReLU activation functions, max pooling 2D layers, and dense layers at the end. The only difference between the two models is in VGG9, we use a kind of classic representation of it, in that we use max pooling on the neural compute stick. Whereas when we have to convert, we actually have to change the max pooling layer to average pooling in order to support it on Loihi and convert it to Loihi. So we have 2 different networks. We have a VGG9 like classical model that will run on the Intel Neural Compute Stick, and then we have a constrained VGG9 network, which just implements average pooling instead of max pooling to be converted into a spiking neural network. So we can convert these things and deploy it on Loihi and get these results and everything now, or we can try to improve the spiking neural network's performance in terms of latency and accuracy. So out of the box, like I said, the conversion process doesn't necessarily yield an optimal result in terms of power or latency gains. The most optimal performance you could get is to design the spiking neural network from the ground up, train it from the ground up. But those things, again, incur a lot of complexity and design challenges. So we can do better with conversion by doing some pre-processing and some analysis to help us kind of achieve a little bit better power and sometimes in some cases a little bit better latency. So we do two different optimization steps. The first one is with respect to accuracy and latency. So because spiking neural networks are kind of temporal based, they require you to kind of optimize how much time you're giving a specific image to the network. So this is kind of called duration, how long the image or input is exposed to this spiking neural network to allow it to kind of propagate through the network and then classify. So in order to do this and optimize this duration, how long we should expose each image on average, we test multiple different sets of durations, and then we search for the best possible outcome. Now, you'll notice in the graph on the right that when we increase the duration, the accuracy goes up, but at a certain point, there's a point of inflection somewhere right around here that allows you to say, okay, well, there's no longer a benefit to increasing the duration. So we need to kind of optimize accuracy versus latency at this point, or duration. So that's what our optimization step does, is it basically tests a large set of durations, and then it looks for a specific duration that achieves high accuracy within 2% of the maximum, while also reducing the durations, which also decreases the latency, overall latency of the network. So after this is done, we have to also test this point, this duration point, to make sure it's not like an overfitted to the test set, for example. So we use kind of a cross-validation, like inspired method, where we split our test data set of the network into 3 chunks. The first 2 chunks, like these gray squares right here of the data set, the first 2/3 of the test data set, are used to try to make sure and validate that these points are actually not overfitted. And then the white square, once we find this optimal duration point, we, with respect to accuracy and reducing latency, it actually allows us to make sure that, again, that point is not overfitted to the test set. And then we do this multiple times, shuffling the data set, making sure that these points are actually achieving decent accuracies and not just fitting to the test data set. All right. And then when it comes to power reduction, we try to incur do some pre-processing, which introduces more sparseness into the input data. So in this case, we use edge detection, specifically canny edge detection, and it trims basically down the amount of data pretty significantly that's passed into the network. So you're resulting with the just edges of a image or item in an image versus the entire image. And because we're still maintaining the shape, we can reasonably probably get decent results while also reducing power. Because again, neuromorphic computing only ever consumes power and energy when there are spikes. So if we can get rid of some of those spikes by introducing sparseness into the input data, that can reduce energy and power. Okay, so as for our results, from our experiments, we could see that the SNN, DNNs, and constrained DNNs all kind of achieve reasonable accuracies, except for the fashion MNIST dataset, which in the edge detection case could not achieve great results in terms of accuracy. But we can see that the CDNN and DNN are kind of neck and neck. In some cases, even the constrained DNN does better in some cases, for example, like this for MNIST in terms of accuracy. And we can even see that the spiking neural network can even achieve a little bit better even. But we also see that edge detection, while it does, we'll see later in the next slide, that it does reduce power and energy by introducing that sparseness. that it does have a somewhat effect on accuracy, marginal effect on accuracy. All right. So, and then when we look at the power and energy consumption, we can see that overall the neural compute stick is more accurate because it's using floating point values. But we can also see that the neural compute stick uses somewhere around 4 to 5 times as much power in terms of like 830 milliwatts or so, versus the power that's consumed by Loihi, which is around 50, 60 to 70 milliwatts. So we can kind of really see the paradigms of neuromorphic computing coming and benefiting our use case for edge computing and vision or image classification tasks here. But we also notice that Loihi right now at least has significantly more latency. So this can be attributed to multiple things, in that one, we're using the conversion method. It's not optimal necessarily. We're fitting basically an artificial or deep neural network onto spiking neural networks and expecting good results. So had we designed this spiking neural network from scratch, we might have gotten better latencies. But when you look at the latencies versus the power differences, the power difference has a much more significant effect, even though you got a little bit more latency. And we can even see that in the energy, that even with that higher latency, energy is still significantly lower than that of the neural compute stick. So with that, thank you for listening. If you have any questions, please feel free to ask. Again, thank you to the IGSC team for inviting us. We really appreciate it.
Thank you, Peyton. Great talk, great presentation. So do we have any questions from the audience? Feel free to unmute yourself and ask your question. Okay, so probably I can start with one question, Peyton. Very interesting talk again. So could you elaborate on power reduction with pre-processing, which you mentioned with edge detection? So as far as I know, you were doing it at software level, right? P4 conversion of the deep neural network to SNN. So it's only for the inference. You don't consider the power consumption for the, like, for example, the pre-processing step or other things, right?
Yes. So it's just for inference. Edge detection, I've seen many papers where specifically canny edge detection is starting to be implemented in hardware as well. So for us to count this edge detection, we would actually have to add the power on. But in the case of a spiking neural network or the DNN, we actually retrain the network so that they would be specific to these cases. But yeah, you're right. The pre-processing step is not necessarily accounted for in our power measurements.
I see. Thank you. So do we have any other questions?
I suppose I can ask. So, hi, this is Alex Jones from University of Pittsburgh. Thanks for a great talk. I really enjoyed it. What I'm wondering is, you're sort of able to reduce the compute to improve the power reduction. One of the concerns that we're starting to see is a big issue is this embodied carbon issue. Is there a way to use this idea to reduce the kind of provisioning required to execute your algorithm, and have you thought about that?
So in terms of like classical deep neural networks or just spiky neural networks?
Well, so you're basically trying to do some pre-processing to improve the performance and energy of the neural network computation. That's my understanding, right? So
yes.
Is there a way to sort of does that reduce the amount of compute effort in a way that you can make the system simpler that could execute the algorithm?
Yes. So Yeah, it should be, it could be, again, since we're converting a network, a traditional ANN or DNN into a spiky neural network, we kind of have to use that conversion tool. Whereas if we were actually designing this spiky neural network from scratch, we could actually go in and optimize the network to where it specifically was using edge detection or some kind of sparse input and stuff. We can actually specify the spiky neural network to even further reduce it, the computation and everything. The issue with that is designing a spiky neural network from scratch is not necessarily a trivial task, because it introduces a lot of design challenges. You have to know a decent background of neuroscience topics as far as learning algorithms such as spike timing dependent plasticity, and all kinds of different design challenges and parameter optimization such as time that cause a huge amount of, overhead in terms of design rather than just converting. If we weren't using the conversion method, we could definitely be more specific to the input data that we give it.
Great, thanks.
Thank you.
Great. So thank you, Peyton.